Right. Welcome back, all. My name is Chris Endemann, and I work as a data science facilitator in the Data Science Hub, and I also help lead the ML plus X community. I'll be kicking off today's event with some small group discussions, and then we will hear from Bella Finkel, who is a math PhD student, and she's going to be talking about detecting or using computer vision to classify gravitational wave modes. The last thing I want to mention before I hand things off to Bella is that we are starting a new GitHub/website that we're going to use to pull together crowdsourced resources. A couple of the things that we're interested in using this repository for, is to post exploratory data analysis examples so people can get a sense for how they should explore different kinds of data. We also want to provide a pre-trained model guide or case studies, because that's a big question nowadays, is which pre-trained model should I start with? There's a lot to choose from. Different applications have better models, or they have particular models that you want to use. There's other resources we can use with this repository for. And so if you're interested in getting involved in this process, we have a few people in the community that are leading this. Please just email me, and we're happy to have you join the team. Okay. So without further ado, I want to introduce our primary speaker for today. So Bella Finkel is a PhD student in mathematics here at the University of Wisconsin-Madison. And today she will speak about her work in gravitational wave astrophysics using machine learning to improve classification techniques for signals from core collapse supernova. So let's give Bella a warm welcome.
Well, thank you very much for your time today. I'm going to be talking, as Chris said, about some applications of machine learning to the classification of gravitational waves that arise from oscillation modes of a protoneutron star that are excited during stellar core collapse. This is joint work with UW-Madison at the Oscar Klein Center, associated with Stockholm University and the Royal Institute of Technology. And I will start by just saying what a core collapse supernova is and why we expect it to produce observable gravitational waves, so that we don't leave these as undefined terms. But then I'll touch on the current frontier of core collapse supernova science and how this work fits into the broader project of preparing for our first gravitational wave detection of a core collapse supernova. This work also presents some challenges and opportunities that haven't really presented themselves before in applications of machine learning to core collapse supernova science. So I will sincerely solicit your opinions and your feedback on this. This is my first work in machine learning, so I do mean it. And please also speak up if you have any questions. So at the end of their lifetime, a massive star that is larger than about 8 solar masses forms a gravitationally unstable iron core. We're looking mostly at these last two sides of the figure here. It collapses until its inner layer overshoots nuclear density and a protoneutron star is formed. So less than a second after collapse, strong aspherical flows arise in the inner few hundred kilometers of the collapsing star. This is known as the supernova central engine. These flows power the explosion and produce observable gravitational waves. While this is happening, the outer core continues to collapse until it bounces off this inner region and launches an outward propagating shock wave. But the shock loses energy as it passes through the core, and eventually it stalls. In most cases, shock revival is thought to be powered by an absorption of a fraction of the neutrinos that are emitted at the core from the protoneutron star behind the shock. This causes the shock to break out the stellar surface and reveals the explosion as an electromagnetic transient. And what we should focus on here is that this is a region that we can't probe with electromagnetic radiation. So humans have been observing core collapse supernovae via their electromagnetic signal for centuries, but we have absolutely no data on these few seconds when we're seeing very exotic behaviors of the protoneutron star. So core collapse supernovae are a multi-messenger source. They give off neutrinos and gravitational waves and electromagnetic radiation. And we're in an exciting time because we're now equipped to observe core collapse supernova with the full brunt of all of these messengers. A core collapse supernova could be the astrophysics event of the century, literally because this is about the rate at which galactic and near galactic supernovae are expected to occur. And when we get this first observation, we'll gain valuable insights into the explosion mechanism and the characteristics of the inner regions of the progenitor star. But to take advantage of such a detection, we need to have some idea of what we're looking for, which is where this work comes in. So if you're doing machine learning and you have at most one sample in your data set, that's abysmal. So for now, our understanding of the core collapse supernova mechanism comes from sophisticated numerical simulations, which have been going on for decades, but as you might expect, most actively in the last couple of decades. The state of the art now includes dozens of core collapse supernova models that span a broad space of both the progenitor characteristics, so their masses, their metallicities, their rotational profiles, and our uncertainties in the physics. In particular, these simulations will use a variety of proto-neutron star equations of state, which is one of the things that we'll be able to understand better once we do have a detection. Importantly, these simulations have been used to correlate spectral properties of the gravitational wave signal with physical attributes of the supernova core. So while core collapse supernovae are stochastic, there are certain analytical relationships we can derive from these simulations. Okay, so I said in this study, we're classifying gravitational wave modes from proto-neutron stars. So in this context, modes is being used in the sense that's common in the sense of dynamical systems. So a proto-neutron star mode is a pattern of oscillation of the proto-neutron star with a characteristic frequency. And what these state-of-the-art simulations have shown is that the excitation of proto-neutron star modes after bounce is the primary source of gravitational waves. So gravitational waves are a good way to study the information these give us. So for example, P modes, these are named, as in other fields, they're named after the restoring force that's bringing these waves back to equilibrium. So P modes, pressure is the restoring force. These depend on the local speed of sound and the size of the region that they're oscillating in, which means that they can be computed using simulation data on the mean density inside of the shock. So the P mode frequency gives us information on the location of the shock. And spectrograms are a good way to study signals from proto-neutron star modes because they show up, right? The modes show up in the time frequency representation of a gravitational wave signal. So I snagged this from the paper that derives some analytic relationships that we use to create our data for this study. I also liked it because this looks sort of like a mask that you could use for like semantic segmentation. It's quite similar to the kind of thing that we are actually using in this study. So another challenge for core collapse supernovae is that their parameters in terms of their time series are inherently stochastic. There's a lot of noise that's physically built into the data and that's built in as when you're using real sensors on anything, noise that's built into the detector. So our preparedness to take advantage of a galactic or near galactic supernova depends on modeling outcomes and interpretation. In particular, if we want to glean knowledge of the proto-neutron star through a core collapse supernova detection, we need to identify how the peak frequency of the gravitational waves evolve, and we need to say where the modes are present in the emission. But this is a prevalent problem because, for one thing, the outcomes of modal analysis depend on the choice of the outer boundary region of the proto-neutron star. So the proto-neutron star is dense, but just how dense is where you define that boundary is up to whoever did the simulation. There are also various methods of modal classification, and there isn't a single one that is used across the board. It's not even clear which one is best to use across the board. So then when you look through the literature, you'll find different groups calling these modes different things. It's not uncommon to see in a paper someone citing someone else's paper and saying that they mislabeled their modes. Okay, so this project is a step towards standardizing modal classification. We want to, for one, train a model to identify the protoneutron star oscillation modes associated with features in the gravitational wave spectrograms. We want to, for one thing, have a model that identifies the modes of which modes are present. And we'd also like to have a model that can tell you exactly where in your signal these modes appear. We also hope to explore which data the model trains best on. So core collapse supernova simulations are extremely expensive. So there's a range of trade-offs that you make when you're given a certain amount of computation time. And one of those things is to make your simulation two-dimensional, to do it in axis symmetry. So two-dimensional simulations are known to be unreliable in many respects for studying the core collapse supernova gravitational wave signal, but they're more plentiful. So we wonder how a model trained on some of this data, which is reliable in some respects and unreliable in others, will train on 3D data, or sorry, how it will be able to interpret 3D data if it's trained using 2D and 1D simulations. And to determine what selection of noise can improve model performance. So how do networks trained on varying levels of noise compare to networks trained on data exclusively with realistic noise? This is a question that's particular to the software that we've developed to generate our data sets, and I'll talk a little bit more about that. So before we began the machine learning phase of this project, my collaborator and I developed a Python package called synthgrav for generating synthetic core collapse supernova gravitational wave signals. So this is a way to work around the small selection of numerical simulations that are available and to use these analytic relationships that we do know exist in gravitational wave spectrograms to predict the gravitational waveform based on physical parameters of the core collapse supernova. So we hope that this will enable us to generate large sets of detailed signal predictions at a low computational cost. So we still start with data from physical parameters of simulations. We start with the shock radius and the mass of the protoneutron star, the central density, and other relevant parameters for how the modes are behaving. But we can broaden the source of simulations because we can now compute a gravitational wave signal from, for example, a simulation that completely computed all these physical parameters, but instead focused on the neutrino signal. So we're further broadening our horizons for sampling data from simulations. Okay, so this is sort of a workflow of synthgrav. Synthgrav takes as input physical properties of the protoneutron star and the collapse that we get from numerical simulations. So we have these physical parameters in time series form. We feed them into synthgrav. And at this point, we have the option to control our noise level and what our noise looks like. So this is noise that's modeling the the stochasticity of the collapse itself. Out of synthgrav, we get a pretend gravitational wave signal. At this point, we have the option of injecting it with real detector noise, so detector noise from observing runs of LIGO, and potentially predictions of noise from other gravitational wave detectors. And this is useful for when we want to study how we would actually do a modal classification for an observation of a real core collapse supernova. So there are several steps where we have options to decide what our noise looks like. These are example spectrograms that were generated using SynthGrav. So these two are fake. We made these with SynthGrav, and this is the real simulation made from the true strain of the simulation that we gained physical parameters from in order to predict these two signals. And I wanted to kind of naively ask, like, if you were in this situation, what are your thoughts? Are there things you would be concerned about with this data? Have you seen other data sets that look like this? Because we're interested in signals that are from spectrograms that there aren't other banks of gravitational wave data, but there are other banks of spectrogram data. It's okay if you don't have thoughts, but what are your thoughts? Go ahead, Chris.
Yeah, I guess it comes down to how much do we trust the simulations, because the simulations have to reflect ground truth, and we have very limited access to ground truth. That's my primary concern. It seems like you have two stages of simulations. I don't think you have any other choice, so I understand it, but it's a concern. Yeah, just because they have to be realistic for the end result to actually work.
Mm-hmm. Please, yeah.
If I understood you correctly, the panel at the bottom is sort of your kind of ground truth, right?
Yes.
And it looks to me like the two top panels are fundamentally different in that the sort of the peak signal kind of bifurcates, right? You have one line going up and another going sort of more horizontally along the bottom. And you don't have that at all, I think, in your bottom part.
Yes.
So that looks like a problem to me.
So these are our intention with these, and I chose some that sort of are extreme examples in the parameter space. But what we do in our actual training is to put masks over where we would say, like, this looks like a G mode. And so we mask where the signal is strongest there. So these would be, this is ground truth in the sense that it's the best gravitational wave signal that we can get. And these are sort of maybe less reliable than a simulation, but it's not the ground truth for the network model. But I still think that you're bringing up an important point, and it's one that we know that there are artifacts from SynthGrav, and that's another thing that I want to talk about in terms of model interpretability and making sure that we account for these artifacts. Yeah, please.
So that bottom one, that's a single gravity wave?
So it's a complete gravitational wave signal from a core collapse supernova simulation. So this is all of the myriad gravitational waves which were produced in the course of a core collapse.
Just because if you have a different signal going down, I don't know if that's representative of subsequent waves that happen in the core collapse, or if that's supposed to represent the totality of it. So, like, the top two, could you have multiples of the bottom one? If that one captures one, but it sounds like that's the totality of the entire event as opposed to one that you're replicating.
Did you have?
Yeah, just a quick question so that my statement makes sense. Again, the bottom is a simulation. The top two are measurement simulations of the simulations. That
yes,
what's happening there?
Yeah. So the bottom one was a complete gravitational wave numerical simulation. Sorry, it was a complete simulation of the core collapse.
Right.
The gravitational waves from the core collapse. Yep.
And then it sounds like you're having an issue in the sense that you have like one or small numbers of actual data.
Right. So.
So my question, when I deal with things like this, I would be asking, what does that sound like? In other words, like, you know, I'm out on the street. If I can knock this down to auditory noise,
Mhm.
what does this sound like out in the world? And then can I go record that and more of it? So then I have real data. And then can I use your simulator and then backpedal into like, to me, I'm seeing an ambulance. I'm seeing Doppler, right? So like, can I go record a Doppler and then like transform it and then have your machine take it apart so that you can actually test this algorithm up against bird noises, for example, or something out there in the world that sounds like this sounds.
That's a really cool idea. Yeah, that's a cool idea. I never would have thought of that, and that's a cool idea. It would be. I feel like it would be cool to even just make sure that it doesn't like it could be. It won't say this bird noise is a G mode, right? Yeah.
Something, yeah, right.
I mean, it raises an interesting. I guess we don't know the domain knowledge on it, but if there's things that are like a star, there's things like a star collapse that
Yeah.
are simpler.
So we sort of did touch on this. How do we mitigate the influence of synthetic artifacts? Especially, this is sort of an extreme example, but the noise. We're still trying to get the noise to look like this noise. We would call this area noise in the simulation. But I think I'm going to stretch over to asking about model interpretability. And there have been other studies that have been have explicitly studied model interpretability on convolutional neural networks trained on spectrogram data. In particular, they looked at how GradCam and ScoreCam perform, or what they indicate about how the models are training. I wonder if you have suggestions for how we can gain insights into the decision-making process of our model, or if there are things we should keep in mind for the model architecture to aid interpretability.
Can you clarify again what the purpose of the model is specifically?
So we want the model to be able to, let's say we feed it this spectrogram, we want it to be able to identify where the emission is coming from a particular oscillation mode. So these labels in the blue and orange are where do we see the signal from an oscillation mode appearing in the spectrogram.
And how were these particular modes identified? Was it by hand? Was it with a different model?
So this is from a paper. So I think this was a person. But the way that we do it is using SynthGrav. So the SynthGrav takes in the physical parameters of the collapse. So for example, the shock radius, we said the P mode depends on the shock radius. So if we feed SynthGrav the shock radius, then SynthGrav will predict us a signal for the P mode, how the P mode is radiating gravitational waves.
So the purpose of this model is to be able to iterate over more real data sets in the future?
Yes, so we'd like to be able to give it a spectrogram and have it tell us this instead of having these be hand labeled. And also, hopefully, so SynthGrav is also giving us physical data, right? It's physically meaningful.
Yeah.
So it can help us to have a standardized way of labeling these modes that has physical meaning. That's not arbitrary. Yeah.
This seems like a really good use case for generative adversarial networks, where you train one network to try to identify which data is real, which data is fake,
Mhm.
and then you have another generator that produces fake data but gets better over time because it's competing against the model that learns to identify what is real and what is fake. In particular, I've heard that in general, neural networks tend to be much more efficient than physical simulations, or at least that's how it's been in like transport research. So you may be able to generate a much larger volume of data, so you can train your classifier model here much quicker and give the rest of the scientific field a much more computationally affordable way to create their own classifiers.
Okay, thank you. Can we chat about that after this? Do you have a few
Absolutely.
minutes?
It would be tough though, because you said there's one of these events once per 100 years or something like that.
Yes, we've never seen gravitational waves from a.
So there's not too much real data that you can feed into the model here.
But the simulations are like, well, they're good in the sense that they have been falsified over time, and there are things that we know are inaccurate. And I mean, there are things that we know are accurate in the sense that they are good approximations of general relativity and neutrino hydrodynamics. So there's only, it's not great, but there's only so much that the physics can lie.
This is kind of out of left field, but would it make sense to, instead of trying to detect this very specific thing, these modes of the GW signals, maybe you just want to detect interesting things in the spectrograms and create a bucket of those interesting things, and then send that to the next team so that they can analyze it for interesting signals.
Yeah, my concern with that is that a lot of the things that would be flagged as interesting are actually noise. And we do know, like, these modes are interesting because they come from the physics of the collapse. So we do sort of know from the physics that these are what we want to look for. Yeah. But it's 1 o'clock, so I'll thank you for your time. Yeah.
Anything else?
I have a bunch of questions. We're all done.
It would be extremely fabulous if we talked. Yeah.
I'm super interested in this. So, of those nodes that you traced up there, how detailed is that node? In other words, what sort of fluctuation do you need to get in order that, like, it's no longer the 2F mode? Like, I'm seeing those little, like, kind of nuanced
Yes.
spikes. Like, you know, do you need, how much of that do you need for it to be a 2F mode? I guess the question.
Yeah, that is a very good question. These are up to 2 sigma uncertainties. I mean, I think that is part of what we would like
To know.
an algorithm to give us, because there are these particular frequency signatures. You can kind of look at it as to what order are you approximating.
Yeah.
So like there are first order and second order features of the individual modes. And that's part of what tells you which mode you're looking at, right? If your mode went down instead of up, then it could
There's the main red line there. There's kind of a flat plateau. You see,
yes.
like, do you need that flat plateau in order for it to be considered a mode of that type?
You don't need a flat plateau in particular, but like if this, another machine learning study investigated what's called the high frequency feature, which is sort of this, appears in this image as the increasing yellow region. And they wanted to estimate what slope this tends to have. And this in total is a combination of modes. It's a combination of G and F modes. But like if you said your first derivative of the slope is negative, then you'd say, well, that doesn't seem like G and F modes.
Right.
Yeah.
How many different parameters are in the simulators? I mean, it sounded like there were a handful of different simulators to begin with, or models.
Yeah, there are a lot, but there are a handful that really utilize the kind of general relativity and magnetohydrodynamics that we would like to see to trust the gravitational wave signal wholly.
Right. And so, like, are you talking like hundreds or thousands or millions?
Oh, I'm talking 10. I'm still talking tens.
10. That's totally legit. Right. That's why I'm asking. Right. And then do the equations have like other forms that allow for some sort of mathematical flexibility so that like, you could increase the parameterization a little bit and decrease the, in other words, move through some sort of lower dimensional isomorphic manifold that's like, hey, we're going to jump up at least one dimension and kind of pop down one dimension and give ourselves a little bit of squishy room here. Or is it, you got to have that, like, are they pretty crystalline in their belief system, if you will?
Wait, could you say again?
Like when you're saying 10 parameters, right? Are these 10 parameters like residing in some sort of mathematical space that's constrained? Is it having like a subspace? Is it a nonlinear subspace? Can you just pull them from wherever you'd like to drop them from? Like, how are these parameters? Are they independent parameters, or like, I'm just kind of wondering about those.
Are you referring to the parameters from the simulation?
Yes, that go into the simulation to create.
That we use from the simulation?
If you go to, remember you have those 3 stacked?
I think it was the core collapse.
Yeah, the bottom one. The bottom one there. To
Yes.
create one of those, how many parameters go into making that thing?
A lot. Well, this is from a simulation that was run on a supercomputer for hundreds of hours.
Okay.
And I'm lucky enough not to be in that line of work.
Right, yeah.
But there are ways that we could there are ways that we can doctor the parameters that we take in. Like the shock radius and the protoneutron star mass and things like that. Yeah.
Just another random thought, but I obviously don't know the background domain, and there's a specific thing that you want to measure, right? This collapse. Is there simplifications in the model or thing you're trying to study that might be informative? You have a whole neutron. Is there like smaller gravitational wave emitters that would be useful to likewise put through this process to validate it of the noise creation? That'd be like easier, right? Like to have an n greater than 1.
Yeah. I mean, you could do something like this for other gravitational wave sources, like compact binary. There's not a need to do it, but maybe if we're investigating what this kind of noise looks like,
right?
then it would give us something to validate at least the noise against. Yeah.
And so even the bottom one takes hundreds of hours.
The bottom.
Even though it's synthetic, it's still worth 1,000 hours or something.
But these took seconds on my laptop.
Right.
Yeah.
Right.
Yeah.
And in other words, the bottom one your field is considered a more true form of ground truthing. I'm not trying to tell. Is that true that it's considered more?
There is nothing else like these in core collapse supernova science. So this was just something. This was more or less an independent research project. I mean, independent from applying using this in the train a model like I talked about.
Yeah.
So this is itself. Yes, this is itself. I mean, you don't want to call it the thing you did in advancement, but this is itself a new tool.
You can call it advancement. That's feel free to do that. There's nothing wrong with that.
It's a cool idea to try to replicate things with other things in the natural world. I'm not sure if anything like that exists. Maybe if you crush a ping pong ball and watch the spectrogram.
I mean, it's to me that I was thinking the same thing. I was thinking stepping on an acorn, but hitting that with an audio frequency seems like, what does it sound like? There's got to be sounds like this out in the world. Like,
yeah,
I mean, it seems to me to be almost like it's increasing in frequency. So wow, 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 wow. That's what that's to me, that's what it should sound like. And that's one of your modes. So out in the world's an exotic place. I mean, supernovas can't be that exotic that nothing out in the world sounds like them at all. I mean, they could be, I guess. I don't know. But
and I mean, they're like, right, you're only capturing a tiny piece of what they are in this.
Right,
yeah.
Right.
Your question about pre-trained models. I know there's some spectrograms, convolutional networks out there that you can download pre-trained. I can't name it. You Google pre-trained spectrogram. I heard for this or
No, but
Gotcha. It's a good option for finding neural networks. That or Keras.
Yeah, that's
It's a quicker option. Keras. Yeah, it's slower to run though.
Can you remind me again why your primary focus is the classification of the modes rather than advancing the time it takes to simulate high quality data?
well, advancing the time it takes to simulate. I would say that we already advanced the time it takes to simulate the high quality data, because these are, I mean, these are high quality. They're just so to make advancements simulating very high quality data is an extremely, that's the primary way that core collapse supernova science advances.
Yeah.
But in order,
Like the dimensionality, probably.
sorry,
There's something to be said about the dimensionality of your problem space, such that like simplifying it is to simplify your model. I have to imagine.
well, it's more like there's a lot of work being done in improving numerical simulations. There's a lot of work being done analyzing the results of numerical simulations. So what this project hopes to contribute to is to improve the analysis of numerical simulations, so that we have a tool that gives us a standard classification method for these modes so that we can fully use the results of expensive numerical simulations to their fullest potential.
So are you grading the simulations or more just saying, okay, here's a simulation and then here's what what modes we think come out of the simulation, or both?
We're only doing the latter.
Okay.
But I'm not opposed to the former.
Okay.
If I can't understand what your question was, it's kind of like the equivalent of like, because I think the weather people do this, where they'll have very advanced numerical models that require a ton of computation. And then on top of that, they have a layer which predicts, is it going to rain in the next 3 hours? You know, and in order to get to that prediction, you need this massive hunk of data, which was synthetically calculated from like last month. You know, so I mean, clearly they're not doing it that long term.
Yeah.
But you got a weather pattern rolling in from 3 months ago synthetically. And now, you know, you want to know, is it going to rain tomorrow? And so the rain tomorrow analogy, I feel like, is what I'm hearing here. We're like, is it going to rain tomorrow? We don't have time to spend back calculating from last month, this big weather chunk moving in, but rather, you know, the question of, is it going to rain tomorrow, being this algorithm, which kind of pops on top of either simulated and or real data. And I'm with you. I also understand I think I'm understanding your perspective, which is, well, if we can just generate this massive chunk of weather data from last month now, then it doesn't matter. But there's always going to be, even if we enhance the computational time, then we're going to reach back to 3 months ago. So we're always going to be faced in this situation where we want to know if it's going to rain tomorrow, whether the data is coming to us from last month or last year. Because whoever, you know, if you can calculate it from 1 month ago, you're going to reach back 6 months and start to calculate, right? Yeah. So there's always this back and forth between this calculation that sits on top. And I feel like this is what I'm hearing.
Yeah, and I want to add that I cut this slide for time, but nope, this is the wrong one. Just look at the same format. But what other studies have done is, in some cases, like in my opinion, is they're doing the best you can, but still some questionable things. It's common to time shift signals from simulations. It's common to perform 2D simulations. So this study had hundreds of two-dimensional simulations that they used. There's also a way you can model gravitational, like the gravitational wave modes as damped harmonic oscillators, which is not physical, but it does model what's actually happening, right? It is it is a damped harmonic oscillator. It's just not that damped harmonic oscillator. So it's a non-physical way. You could maybe this is sort of like a non-physical version of what we do, but what we do is physical, and it is fast. And it's also something I'm interested in to maybe include some time shifted signals and throw some of these into our training set too. But yeah, I SynthGrav solves some of the problems of these where you're either too inbred, you're not diverse enough, or you're you don't have a physical meaning to your signal.
I also wonder about the noise in the model. Like you said, it's stochastic noise and just random noise that you add on top. Is that right?
Yes.
So, but you also mentioned that in the real data, there's a lot of noise events that kind of look interesting or look like features, but they're just noise. So it sounds like there's different events out there that can be detected and measured. And if that's part of the real signal, that's not captured by your simulations, then when this goes to be applied to real data, the model's going to be really confused when it sees other sorts of events or really specific kind of that aren't captured by your noise model.
Okay, I mean the noise model that we're using in the simulations, at the moment we're still working on it, but at the moment, and again, this is somewhat of a pathological example, but this is the real simulation, and this is the synthetic signal, and for the most part, we just end up with emission with a noise signal down here that we don't see in most real models. And I could imagine, honestly, I thought about like taking a paintbrush and just but yeah, does that sort of speak to your concern?
Well, I mean, it makes me want to go back to trying to almost cluster the data that you do have that's real to try to figure out what are the interesting signals in the real data. So find those clusters, and then of that cluster, where are the gravitational waves, and then what is everything else? It's the everything else that's maybe not accounted for in your current simulation procedure. There's going to be other events that are mixed in.
Do you really only have 10 real events? Like actual measured, or there are no,
There's zero. Yeah, there is zero.
N of 0.
But there are,
This is the best kind of data science problem ever.
I mean, yeah, but there are, I mean, let's say I emailed 50 people asking for their data,
Right.
and there were an average of probably it's like 3. And let's say for each of those people there were 3 simulations. That's something like the number of numerical simulations that we're looking at.
100, 200
Right.
ish.
But of those, a lot of them are obsolete, at least in some respects, right? And we can tell the respects in which they're obsolete and which
Sure.
respects we expect them, in which respects we expect them to be accurate.
Yeah.
Yeah, sorry, go ahead.
No worries. Forgive me for not quite understanding it on the pipeline side. Are each of these simulations de novo, or are they variations on the existing simulations that they're out about?
I would call them variations on the existing simulations, but we can, so something that we can do is we can use a simulation where we didn't see significant emission in one mode and imagine that we did. So SynthGrav can take the parameters from that simulation and say what that mode emission would look like.
So the variations that it's based on, so it's not de novo, do they bring their own noise to the table?
Not more, no, not more than, yeah, not.
Because if you're adding in noise on top of more noise, the pre-existing noise, I can see how that could create problems. Like this bottom one, for instance, right?
Yeah.
The simulation. Is there noise randomness added to those? I don't know how that manifests particularly in the simulation, but I have to imagine that there's some parameters, stochastic, some randomness, right? Like in it. Sure. And if you adding randomness to existing randomness, then you're like multiplicative as opposed to just additively adding on top of it. So I don't know how much of a problem that potentially is.
No, that's an interesting point.
I don't know if they're like, they come up with the spectrogram. Is this the end product of the simulation then, these spectrograms are made?
It's one of them, yes.
Cause I don't know if, when they hand out the spectrogram, if they've added, oh yeah, in the spectrogram, we expect to see these kinds of errors and we've added it on to the end of our simulation. And the spectrogram that we're feeding it. I can see that as something they might do.
Yeah, I think it's an interesting question where this stochasticity is coming from if you're already using and so there's noise built in from the time series parameters that you get from the simulation, like on the shock where the shock radius is. I mean, part of this is merely visual, right? We're like, I want it to look like that.
That'd be great. Yeah. But I don't know if you wanted, like, you've given that, and I imagine that there is some mathematical pure idea of the expression of the wave, right? For at least your process, it seemed like it would be better to start with the pure mathematical expression of whatever this process is, and then noise is added on top versus taking something that created a simulation of it and then adding noise to the simulation. I don't know if that made sense.
Yeah, I'm not sure in what ways that would be possible, but I think
Because you drew the line, right? Like you drew the F line, the G line, or whatever.
Yes.
That's the pure expression that's like there that you are just detecting. And so to me, it would make more sense if you took that and added noise to it than this pre-noise thing.
Yeah. Well, that is, and I mean, SynthGrav lets us control how much noise is in the, like how much noise we add on, right? There's a noise parameter in SynthGrav, so that if when we turn it off, we get something like the top panel here, which is
A little cleaner, right?
yeah, and it's still distinct. Right, we can still broaden our data set this way and get distinct signals.
Yeah. Awesome. Well, thank you so much.
Yeah, thank you.
It was a really great talk. Thank you.